This is AP Physics, back to pondering series and parallel circuits where we left off on Friday. On Friday we had gone through the basic relationships, and then we analyzed a simple series and a simple parallel. So we'd gone through and calculated values for each of these circuits. They have the same batteries, the same voltage, and then the same three resistors. One is series, one is parallel. We got these values, and we're getting ready to draw conclusions on these. If you look at your values here, equivalent resistance for series, equivalent resistance for parallel. Well, when you add resistors and you're in series, that's more obstacles. So then the equivalent resistance is driven up. When you add resistors in parallel, that's more branches. And so the equivalent resistance goes down because there are more paths by which those charges can move. Following directly from that then, your current in series, if you have a higher equivalent resistance, then you're going to have a lower total current. And remember that current then in a pure series is constant. So everything gets less current when you're in series. In parallel, because you add more branches and the equivalent resistance goes down, less resistance means that your total current goes up. Each resistor, okay, 1, 2, ... whatever, they have different resistances in their individual branches, so those values are going to vary. Okay, voltages in parallel, each resistor has its own individual path to the battery. That means your voltages on each resistor are constant. In series, though, with the same current and different resistance values, your V values will vary. In the big picture, a lot of times we put resistors in different combinations of series and parallel because there are only certain values that are manufactured. And if you need a different value, then you just come up with a network of a few resistors of values that are manufactured to get the specific resistance value that you need. Now, considering more complex circuits, here we have a circuit that is a combination of series and parallel. And anytime when we get to problem solving, feel free to pause the video, work out the problem. I will continue on and talk through and work through. So, first thing I would do here is to redraw my circuit. So start with my battery. I come off the battery and I get to junction A after I have a resistor in there. So if I put a resistor in there, R1, 3 ohms, and then we get to junction A. At junction A, we have some choices. Okay, from A, I can get down here to R2. I can also get to R3, and I can also get to R4 without running into anything else. The fact that it branches right here at point C doesn't make a difference. Those are only wires. So we have access basically from point A only on wires to any of those. So that means when I redraw, the way I'm going to redraw that from location A here is I have 3 possible places I can go. One of those takes me to R2, which is our 9 ohm resistor. The next one takes me to R3, which is a 4 ohm. And then the next one takes me to R4, which is a 6 ohm. After that, all of those branches from here, I can get to location B From there, I can get to location B, and from here I can get to location B. So that means on my redrawing, I'm going to join all of these wires together, and I'm going to call that junction, junction B. From there, from B on the top diagram, we get all the way back to the battery. Okay, and so that's the circuit. Overall, it's a series circuit. R1 makes it series because I run into that off the battery before I run into anything else. And then R1 is followed by a little parallel network of 3 branches, each branch having a single resistor in it. So then looking at the quantities we're trying to find, first thing I would find is the parallel resistance. So if we consider the parallel network, that's an inverse equation. So 1 over R for the parallel would be 1 over 9 plus 1 over 4 plus 1 over 6. Doing the math and solving that down, I get a 1.89 ohms. Anytime you find a value, always put it onto your diagram because you're going to need it later. So 1.89 ohms takes the place of everything there between the lines. So then that means our equivalent for the entire circuit. Now I have a 3 and a 1.89 ohms in series. And in series the resistances add. So our equivalent is 4.89 ohms of resistance. Now, finding your current. Ohm's law, V is equal to I times R. So I total would be V total over R equivalent. So that's 24 volts over 4.89 ohms, which is going to give us 4.91 amps. Once you found the totals, go and plug in anything that is constant, or fill in anything that's constant. Okay, the only thing we can fill in that's constant is I1, because all the current from the battery has to go through I1 or R1 to be able to get to anything else. So I1 would be the 4.91 amps. Okay, then it splits up, and so there's nothing else we can fill in without calculation for now. V1 would then be I1 R1. So that's going to be your 4.91 amps multiplied by 3 ohms, and that's going to give us 14.72 volts. Now, next thing on our list down there would be V2. And looking at V2, because you're in a parallel network, V2 and V3 and V4 are equal. Each of those are only equal because they're in parallel and because there is a single resistor in each branch. So they have to be equal to each other. So then I can go I times R for the entire parallel. So if they were all one single one, all the current of 4.91 amps would flow through. And if they were all one resistor, that would be a 1.89 ohms. Okay, so when I multiply those together, we get 9.28 volts. The other way you could have done that was you had a 28 volt battery. You already accounted for the 14.72 volts across resistor 1. 24 volts minus 14.72 is going to give you the 9.28 volts also. Okay, now we found something. We're going to put it on the diagram. So on my diagram, in parallel, volts are constant. So I know in branch 2, 9.28 volts. In branch 3, 9.28 volts. In branch 4, 9.28 volts. It's good to draw your diagram a little big so things don't get crushed on there. Okay, now we can fill in V4, 9.28 volts. Okay, I3, because we've got written out there already the volts and the resistance across R3, I3 Ohm's law is just going to be V3 over R3, which would be 9.28 volts divided by 4 ohms. And that's going to give us a value of 2.32 amps. Now, power on number 4. You've got 3 power equations. I squared R, V times I, and V squared over R. It really comes down to whatever you know enough to calculate the easiest. On resistor 4, we have labeled on our diagram V and R. So then I would probably go, power 4 is a V squared over R, and that's going to be 9.28 volts, and that's squared over resistor 4, which is 6 ohms. And when we do that, we get 14.35 watts. Okay, so again, whatever you're finding, redraw the circuit to emphasize series and parallel, find your totals, fill in what's constant, and then piece by piece rebuild and go through the circuit to find the different parts. Now let's consider another example. Okay, if I was redrawing this one, okay, first of all, I see 2 batteries there that are in series. In series, the charges are going to have to go through each battery. I'm just going to draw it as one battery, and in series, those would add together, so that's 15 volts. Coming off of one side of my battery, the first thing I run into is R1. Because I run into that, that tells me I have an overall series circuit. After R1, we break into 2 branches. Down the first branch, I have R2, and that's 9 ohms. And then on the other branch, I have 2 resistors. Before those 2 join back up, R3 at 7 ohms and R4 at 11 ohms. And then after they join back up, we run into R5 at 5 ohms, and then we head on back to the battery. So R1 and R5, either or both, make it a predominantly series circuit, and then there's the little parallel that is between them. So if we're going to calculate the equivalent resistance, okay, I'm going to start with the parallel, just like we did on the last one, only because it's the smallest element. And actually, before we get to the parallel, we're going to do one other thing. We're going to take care of the little series of the 7 and the 11. So the 7 and the 11 combine to give us an 18 ohm resistance. Okay, and so then in parallel, 1 over R would be 1 over 9 plus 1 over 18. Common denominator would be 18. That would be 2/18 and 1/18. That would be 3/18. Inverted would be 18 over 3, which would be 6 ohms. So then my parallel can be replaced by a 6. And so then our equivalent would be the 3, the 6, and the 5 all in series. So that gives me 14 ohms of equivalent resistance. From Ohm's law, V equals IR. I total would be that V total, or that EMF, over our equivalent. So that's going to be 15 volts over 14 ohms. And that's going to give us a value of 1.07 amps. Immediately fill in anything that's constant. All of the current will go through resistor 1, so this is going to be a 1.07 amps. And we're not asked to find I5, but I'm going to go ahead and note it down here on our diagram that the current going through this is the 1.07 amps. Now from that we can immediately find V1 and V5. That's just an I1 R1, and then on 5 that would be an I5 R5. So then on V1 that's 1.07 amps times 3 ohms, which would be 3.21 volts there. And on V5 that's going to be 1.07 amps times 5 ohms, which is going to be 5.35 volts. Now, next thing we get to is the parallel network. In the parallel network, voltage splits, okay, or voltage is constant. But to be able to find that voltage, I'm going to go to the entire parallel. So if I go V equals I R, the I, if I only had one resistor there, it would be the 18. And if there was only one resistor there, all the current would flow through it. So 1.0, having a little trouble writing here, 1.07 amps multiplied by that 18 ohms will give me the volts across the parallel. So if we go for a bright color, we can see that volts across the parallel is going to be 6.42 volts. Now I can't say that that's V3 and V4 because part of it on each, but V2 would be 6.42 volts because there's only one resistor in that parallel branch. Okay, now we'll change from the obnoxious color. Next thing we want to find is I3. Well, I3 is going to be the same as I4 because they're in a series on that branch within the parallel. So that's going to be V over R for the branch. So V for that branch was the 6.42 written on the diagram, and R for the branch is that 18 ohms. So then I in that branch, when we divide, 0.36 amps, so we can fill that in for I3. And then the only thing we're left with is V4, and nowhere to write. So if I want to find V4, I4, R4, we already know I4 because it's the same as I3, 0.36 amps. R4 is then 11 ohms. So when I multiply those together, we get V4, 3.96 volts. Now, kind of in summary, okay, in a simulation, a series circuit. Here we have a simulation of a series circuit whereby your battery is being represented over here, essentially like an elevator, pushing the charges, okay. The wires then, this would be a wire, right up there so you can actually see it. This would be a wire, okay, between your resistors, that would be a wire. Your turning wheels would be a resistor. So you'd have two resistors, okay, and each of those resistors are impeding those charges from moving. Different values. Your 30 ohm resistor is taking more, using the gravitational model, more gravitational potential energy. The charges go down a big hill. Okay, the 10 ohm resistance is less. Okay, so this is analogous to a school building whereby if you got on the elevator outside my old room, you'd go up to the second floor and then you could come down to the first floor, by going down several different flights of steps equivalent to different resistances, but you get all the way back down to the low potential, and then the battery would raise you back up to the high potential. In side note here, if you notice on the animation, positive charges are moving. We know we don't rip protons out of the nucleus of an atom, okay, but just like for an electric field, we use a positive test charge. For the direction of an electric current, we also typically denote it in terms of the direction a positive charge would go. So it's basically the electric current is opposite to the direction that electrons flow. Parallel. Here's your same two resistors in parallel. Okay, your charge is split, and notice when they split right there, they do not split equally. They're taking the path of least resistance. So your 30 ohm resistor would be analogous to a very narrow stairwell. Okay, your 10 ohm resistor, a very wide stairwell. So more of the charges go through, okay, the 10 ohm resistor. It's the path of least resistance. Which path they go to has nothing to do with how close it is. Has everything to do with what the resistance is. That's more complex series in parallel. Tomorrow we will ponder Kirchhoff